When it comes to generic graphs, which is what we've got listed over here, just a basic y equals x to the fourth, y equals x squared, y equals x. So there are patterns that these graphs have set. Like for example, the purple graph here is the y equals x line. Our red graph here is y equals x to the fourth. Our blue line is y equals x squared. So these are things that you're used to seeing, like parabolas or things like that. Um, this brown line is a graph of a logarithm, which is listed right here. And we got an example of a graph that's a decay. So just a quick review on what these things look like. And the reason why we're going to review what these things look like is as I go to this graph here, and if I were to trace the curve, it looks something like that. Now, that's nice to see because if I go back and then I use a curve and trace it, it seems to match up with a couple possible options here. This curve is very similar to this curve, which is our log curve, and it's very similar to this curve, which is our square root curve. So then let's transform our explanatory variable by taking the square root. Now if you notice, our R value is 0.73. After square rooting the explanatory, our R value has increased. So in other words, we made it a better relationship. But if we take the log of our explanatory, it even gets better. Because remember, back on this page, these two graphs were similar to the one that we actually had, square root log. So if we try the square root, we get a stronger relationship. But if we try logging it instead, we get an even better relationship. But let's log the response. Sorry, we have 1 over the square root of our explanatory variable, which makes it even stronger. Now, the reason why I'm kind of showing you these different things in the process is that when it comes to transforming data, there's not a set rule. You transform data in however way you need to transform the data. There are some hints, like for example, bacterial growth is nature. And a lot of times when we see nature, we use logarithms, whether it's the logarithm base 10 or the natural logarithm. So then when we talk about a linear graph versus an exponential graph, linear growth is like your paycheck. If you work 10 hours, you get paid $20 per hour. You know you get 200 bucks, period. End of story. So linear is kind of like your paycheck example for linear. An exponential example, well, that's like where we see think of bacteria, where bacteria will double, or your cell growth, because your cells double, and then they double, and then they double. So in that particular case, the percent would be 100%.